All right, welcome back. Hopefully, you are listening to me at 2x the speed because I feel like I talk very slowly when I'm recording myself, but I'll try to make it just a little bit more quick. So, the first thing that I want to talk about is now that we have the deformation gradient, actually, we can think about taking gradients of other things and not just the deformation. So, what happens if we have some scalar field A in terms of x and we want the corresponding field in the deformed configuration? So you can think of having, again, you have your reference configuration and then you have some scalar field. So this is some scalar field, right? And so that just means that we have, you can think of having the contour plot of some scalar field. Just having fun painting in the deformed configuration, and then you have the deformation map, right? And then that deforms the thing. So we have B, and then as this thing gets deformed, then we are mapping the same scalar field, but now it's a little bit distorted because we have just distorted the geometry a little bit. But it's the same field, right? So the same points have the same information. So the point X here that gets mapped to this point here has the same value. The point that was here that gets mapped here has the same value. So the points keep their value as they are moved. So we have this scalar field, and this is where it becomes important that if I have the scalar field expressed in terms of the reference coordinates, so in terms of this x, capital X, or whether I have the scalar field now in terms of the other coordinates. So I can think of this scalar field in terms of the deformed coordinates, but it's the same field, right? The only thing that it's between them is essentially a composition with this map. So I just have, if I take this field which is in terms of defined here, so this is sort of naturally appearing here, and this is sort of like what I see if I look at this deformed body. Hopefully that makes sense. So this is sort of this capital A is sort of what happens if I'm looking, if I'm measuring things looking at this, whereas this one is sort of what happens if I am looking at this other part. Hopefully that makes sense. And you can hopefully also see that this is the same. So this is, again, the only thing that is different between them is that I'm composing with this deformation map phi. So this is the same as A composed with the inverse. Actually, if you think of this as having an inverse of little x, right? So if I take this field and I just compose the little x with the map, then I'm gonna get back to the to each other one, right? So this is, I'm gonna get back this scalar field, right? Which is the same that would happen if I compose this with, so instead of little x, because I know little x is basically the formation map applied to x, then I can compose, right? Because I have this, I know this, or in this case I know x equals phi inverse of little x. So that's all I'm doing here. Basically just composing with the map. Well, in this case composing with the inverse map, or in this case composing with the map, right? And so what happens if I want to take gradients with respect to the coordinates in the reference configuration? So what happens if I want to take a gradient that is with respect to this, a gradient in this body, right? So that would be the gradient of A, which is going to give me some vector field, and in components, so this will be the partial derivative of A with respect to capital X I, right, in components. Because the scalar field with respect to the x gives me a vector field. And then what I want to know is what if I want to take derivatives with respect to in the deformed configuration. Obviously, there's some relationship, but they are not actually the same. So this would be the same as doing this is the same as doing the partial derivative, this partial derivative, but this is the same as doing the partial derivative of a, which is in terms of the little x, with respect to little xi, and then the little xi, actually, let me call this j, and partial derivative with respect to capital Xi. The reason why I need to name this I is just because this one is the free index, so I need to respect. So whatever here, this is the free index. Whereas the other one is a dummy index, so the J is dummy. That's why I write in yellow, so you cannot even read what I write. So that's why I need to use a different. It could be J, K, whatever. So that's it. I just use the chain rule, and this is because it's the same. It's the same scalar field. It's just parameterized with respect to the capital X or the lowercase x, right? But now let's write this second part in tensor notation. So this was in components, right? Let's get back to the tensor notation. So this part right here, that one is the gradient of a with respect to the lowercase x's, right? So this I'm gonna call gradient with respect to the lowercase of a, and then this right here, it's almost the deformation gradient, right? But the only thing that happens is that the deformation gradient has to be contracted with this field on the first index, so there's a sum implied here, right? So there's a sum over j. Sum over j implied. So here I am using the summation convention. And because of that, actually, it's not f, but I need... So either I have the transpose of the gradient times f, or I have the transpose of f, because this thing right here, this is f, right? Or almost f. And so I need to make it transpose. And that's just because the index that needs to be summed over is the j. So either I do little x a transpose f, right? So that I can get rid of this, but this doesn't really makes a lot of sense, because this is a vector field, so I really haven't defined transpose of vector fields. I have only defined transpose of second order tensors. So actually what makes most sense is to transpose the tensor and apply that to a vector field. So that's just why I transpose the f. So what we see now is we have a relationship between taking gradients of a scalar field with respect to the reference coordinates capital X and the gradient of a scalar field with respect to the form coordinates lowercase x. So that's exactly what we have done here. And this is why I have in the title gradients and gradients. So sometimes you will see this expressed as capital case gradient of A equals F transpose lowercase gradient of A. But all this means is whether I'm taking partial derivatives with respect to the capital X or the lowercase x. So this one is important. Now that we have the deformation gradient, we can do that. And then another one is, what if I don't have a scalar field, but I have some vector field? So again, I have some, gonna copy these. So now I have a vector field Well, I'm not gonna use the contour plot. I'm just gonna use little arrows. And then again, here I'm not changing anything about the vector field. It will look exactly the same. It's just gonna move a little bit depends on how I deform this. Basically just the exact same thing. So I have some vector field W in terms of the capital X, right? And that one will be the same as I can substitute the capital X with the inverse deformation so that I get something in terms of lowercase x, or I can define this sort of like a lower w in terms of x, right? Which is the same as w in terms of phi of x. So these are all sort of the same field. This is exactly the same as what I was doing here. So, but I think with the scalar fields, it might be a little bit clearer that the point, every point that I track here has the same value. So same here, every point that I track has the same vector associated with it. It's just that because the points get moved because of the deformation map, then the vector field seems to be a little bit stretched and moved around. But it's the exact same idea. So I'm gonna do the same. So I want to calculate the gradient with respect to the capital of this W, right, which is defined in terms of the capital X. And so in components, this will be a second order tensor, because now I have Wi with respect to xj, right? And then what I'm saying now is that if I have composed this, if I have the same, this is the same as this other vector, a vector field. So then I'm gonna do partial derivative of dwi with respect to lowercase. So this w is in terms of the lowercase, and here I need to use a different index. I'm gonna use k, and then dxk d capital X j. And again, I need to keep the free indices the same. So I needs to match the I, j needs to match the j, and then there's a sum over k implied here. Right, and we do this because of the chain rule. And let's go back to the non-component part. So this is clearly the gradient of the vector field in with respect to the lowercase coordinates, and then this is again f. So now this actually is f. So we don't need to transpose because this makes sense. So this is second order tensor applied after another second order tensor. So here I don't need to do the awkward transposition that I did last time. So the gradient with respect to the capital case of w defined in terms of the capital case x is going to be the gradient with respect to the lowercase x of this w, small w, times f. And so here it makes sense because that's why I don't need to use the transpose, because here it's, second order tensor applied to second order tensor. The reason why I had to change the before is because it doesn't make sense to have vector times second order tensor. So that's why I transpose the f. So I have again second order tensor times vector, which makes sense. All right, so this is the relationship between the gradients with respect to the reference configuration, or gradients with respect to the deformed configuration for vector fields. So that was another thing that I wanted to talk about. And the reason why I needed to introduce this is because it's needed for the rate of deformation, as we will see in a sec. So that's kind of, we need to be able to take gradients, because now I want to talk about rate of deformation. So last time I introduced the velocity and the acceleration fields, vector fields. But now what if I worry about not just the fact that, points are moving or the material is moving, but I want to know about the strain rates, for example. So as you can imagine, that's going to be related to the rate of change of F. So basically what I want is I want F dot, right? And that one will be the partial derivative with respect to time of F, and that will be the partial derivative with respect to time of the partial derivative with respect to the big X of the deformation map phi. In this case, we can exchange these derivatives because the X doesn't depend on time, they're independent variables. So this is equivalent to the partial derivative with respect to X and partial derivative with respect to time of phi. And this is the velocity vector. So this is partial derivative with respect to X of velocity. So phi dot is the velocity, right? And this is the gradient. So F dot is the gradient with respect to the capital X coordinates of the velocity vector field. So this one is important. And the question here is similarly to what we did for velocity and acceleration. When we talked about velocity and acceleration last time, we asked, okay, what if I want the velocity not in terms of the the reference coordinates capital X, but what if I want it in terms of the spatial coordinates lowercase x? So the same thing here. So what if I don't have the velocity in terms of capital X? So I cannot take the gradient with respect to the capital X. What if I have the other field, the velocity field? So the spatial velocity field which we define as v hat, which was in terms of the spatial coordinates, lowercase x. So what if I have that, and then all I can do is take gradients with respect to this lowercase x. And so what we just did is, so what is the relationship between gradients of vector fields in the reference configuration and the gradients in vector fields in the deformed configuration? So we just did that. We just said, the gradient of W in this case with respect to the reference coordinates is going to be the same as the gradient of the lowercase vector field with respect to the lowercase x times the deformation gradient. So all I have here is that the gradient of the velocity vector field, which is in terms of this capital X, is going to be the gradient of this same vector field. It's the same vector field, it's just that it's in terms of the lowercase x times f. Right? I just used exactly what I had derived before. And this is equal to f dot. And this gradient right here, this has a special name. This is called L, which is the spatial velocity gradient. And that is then the notation for spatial. So typically we refer to things as either reference if they are in terms of the capital coordinates, capital X, or spatial if they are in terms of this lowercase. So if they are defined so this is not just reference and deformed configuration, but this is also called spatial configuration. It's basically what we observe. Yeah, so this is called L. So if you can see from here, another way of defining L would be, which is the gradient of this v hat in terms of little x is going to be F transpose F inverse. So that's another one that is important. Again, typically we're not going to be so interested about the rate of the deformation gradient itself, but rather what we want is strain rates. So what if we want strain rates? Then what I want is for example, E dot. So the rate of change of the Green Lagrange strain tensor, which is the same as 1/2 C dot, which is, so if you remember, I'm gonna say recall, E equals 1/2 of C minus I equals 1/2 of F transpose F minus I. So I want the rate of change of that, which is equal to the half the rate of change of C, which is going to be half of, if you take the time derivative of this, you're gonna get F dot transpose F plus F transpose F dot. So just product rule for that. And so that gives me the strain rate in terms of reference quantities, right? And I know that will make a little bit more sense later on. For now, can we just trust me that there's things that are more naturally associated with the reference configuration. So C and E are more naturally associated with the reference configuration, whereas things like L, I should actually put the tensor here. L is more naturally associated with the deformed configuration because it comes from taking spatial gradients, right? Gradients of things that are defined with respect to these deformed coordinates little x. So that's just it. In terms of what got parameterized, in terms of what variables, it's the same field. So the velocity is the same velocity. It's just whether it appears in terms of the reference coordinates capital X or the lowercase deformed coordinates, so deformed space. Again, I'm really hoping that this image here will convey the point that the same thing happens for vector fields, but probably for scalar fields it might be clearer to see that it's the exact same scalar field. It's just it got stretched out a little bit when we deformed the geometry a little bit. That's it. So the same thing for the vectors, these vector fields. The velocity in the reference or the deform is the same vector field. It just got squished out a little bit with the deformation map. But because of that, we can do operations in the reference configuration or in the spatial configuration. And so here E, for example, E dot is associated with the reference configuration. Whereas if we want to have things in the deformed configuration, what we can do is we can plug in the definition, so we can use this equation right here to see that E dot is going to be equal to F transpose 1/2 of L plus L transpose times F. That's just from sort of plug this in here, rearrange things a little bit, and then you're going to obtain this. And this has a special name. This is D, which is the symmetric spatial velocity gradient. Because 1/2 of L plus L transpose, that gives you a symmetric second order tensor, so this is the symmetric spatial velocity gradient. And we'll see that one is related to basically the equivalent of strain rates in the deformed configuration. So we have, E dot equals F transpose dF. Or you could write the opposite, right? So you could write D in terms of, like we did here. You could write that as well. So you could say D equals, well, I guess the simpler way of doing it would be 1/2 of L plus L transpose, because then we have things that are in terms of spatial quantities. So L is in terms of spatial quantities, right? And then if you rewrite it from here, you will also see that D equals F minus transpose E dot F inverse. But I would say probably these two are the most, and probably this one is the most important. So that's it, and I think that's all I wanted to cover. Basically, just rates of deformation, and because of those rates of deformation, I needed to introduce this notion of how to take gradients in the reference or deformed configuration for scalar fields and vector fields. And I really hope that clarifies this idea that it's the same scalar field, the same vector field, it's just composed with a deformation map. And then you can use that information to get these strain rates